Pradeep sir, am I audible to you?
Yes, yes, audible. But your sound is little low level. The level is little low.
Now it is okay.
Relatively better.
Okay, sir. Let others join. Then we'll start the session from 6.
Okay. So this is the first session or the last session? Hello.
Good afternoon, everyone, and welcome to our ATAL Faculty Development Program. We are in day 4 of this online ATAL Faculty Development Program on next generation communication. Our faculty development program titled New Next Wave Advancement in Next Generation Communication. Today, I am going to. Am I audible, sir? Am I audible to all?
Yes, yes, audible.
Okay. Today, here with me, Mr. Joydeep Nath, uh, who will take the session 7, who is the senior consultant engineer and academics in logarithmic Consultancy Private Limited, Kolkata. He has 30 years of experience. Let me introduce him. Uh, it is our privilege to have Mr. Joydeep Nath. He is a BTech in Electronics and Communication Engineering from the Institute of Engineers in the year 1994. Before he completed his graduation in Basic Science from University of Calcutta in the year 1987, he started his career in 1995, and 1 year after starting, he joined Ericsson as Quality Control Officer in Technical Division. His responsibility was performance and quality checking of various imported communication radio set mainly used for Indian defense sectors. Since then, he gradually engaged in his research activities, especially in communication engineering and amplifier embedded system domain. During his career in Ericsson, he was the active designer for developing indigenous communication kit for defense uses. He was an expert design contributor in developing the kit. In the year 2007, he turned into automation field and joined a Calcutta-based automation company. From 2007 until 2022, he dedicatedly worked in automation field in PLC, SCADA, and drives. And besides this, he developed various tailor-made electronics gadgets using embedded chips and VLSI chips. He also establishes an advanced communication lab in NIT Rourkela using HDR, NIUSRP, LabVIEW, and MATLAB. He conducted data acquisition workshop in IIT Patna, NIT Silchar also. Developed a data acquisition portable kit using NI hardware and laser developed sensor in Civil Engineering Department of NIT Silchar. He successfully completed 2 PLC projects in material science and cyclogenics department in IIT Kharagpur. He also developed a panel for negative pressure cooling system work using NI hardware at mechanical department in IIT Kharagpur. Now he is engaged in developing projects, especially in NITs and IITs in the field of communication, embedded system, automation, and VLSI. He also earned many contributory awards from NITs, University of Calcutta. His rich experience and deep concept of for various fields of electronics is an asset for his company. His current area of interest is mainly FPGA chip programming and AI and machine learning. Now, today he will discuss with us about the software-defined radio application in advanced wireless communication. So, after you, sir, Joydeep, sir, please take the session.
Okay.
We are starting session 7. Welcome, sir.
Thank you. Thank you, Pradeep, sir. I'm very proud for you. And it's a rare privilege to give a lecture in such distinguished persons. You have explained all my workings over VLSI, embedded systems, machine learning, and everything. Now, I am Joydeep Nath from Logarithm Consultancy Private Limited. It's a basically cloud-based company, and we work in cloud infrastructure and instrumentation. My department is instrumentation and analog circuit and digital circuit design, and we especially work with NITs and IITs. I have been invited by Mr. Pradipto Maiti for this lecture. about the SDR and advanced communication system. Now, I divided my lecture into three parts. First, we'll discuss about wireless communication and its types. Then SDR, I mean software defined radio, and its basic architecture, application, and after that, advanced wireless communication research lab. So what we do with SDR and what is the purpose of SDR? Nowadays, it's a very common term, SDR, software defined radio, how it works and what is the basic function and the technology related to SDR. All we'll discuss for today's seminar. And at last, we have three questions for the student level, which is a very basic one, will be given at the end of the session. Now, can I share my screen right now? Just hello.
Yes, sir. Yes, sir. You
Just a minute. The screen is visible. Hello.
sir, the screen is visible.
Visible, na?
Yes, sir. Yes, sir.
Okay. Okay. Now it is seen.
Yes, sir.
The software defined radio in advanced wireless communication system. I just give some little idea about the wireless communication system and its type in the first phase of discussion. Now, wired introduction to the wireless system, how its inception and its growth and process and time to time situation. Now, wired network is a bounded medium where data travels over a path that a wire or cable takes. In modern era of advanced and enormous number of devices, wired medium of communication imposes a restriction on fluent communication. We know everybody that with wires and is a wire network, it's making many kind of problems during the transmission part, and there is a tear and torn of the uh, wires make lots of problem for the communication purpose. So that in the modern era of advanced and enormous number of devices, wire medium of communication imposes a restriction on fluent communication. Consider a situation you want to connect to 10 or more devices around you. You need exact same number of ports to be able to connect to the devices. Very usual. But large number of ports seems to be impractical, but with wireless network, it can be easily done. As the name suggests, wireless network eliminates needs to be tethered with wire or cable. Now, wireless communications is a transmission of voice and data without cable or wires. The first wireless transmitters went on the air in the year around 20th century. Hello, hello.
Uh,
Can I continue?
yes, sir. You can.
Okay. Using radio telegraphy, well known as Morse code. Later, a modulation made it possible to transmit voice and music wirelessly. The medium became known as radio. So wireless transmitter use electromagnetic waves to carry voice data, video, or signals. The groundwork for modern wireless network was laid in the early 1970s with the launch of Aloha Net in Hawaii. Just a minute. Aloha Net in the Hawaii. The additive links on online in Hawaii. Hawaii island. The network, technically a wide area network, relied on ultra high frequency signals to broadcast data. Only data was there. The technology underpinning Aloha Net helped fuel the creation of Ethernet in 1973. or 73, 74 around this time. Aloha means additive links on line in Hawaii. Hawaii is a kind of, everybody, Hawaii is an island, volcanic island. But the wireless experiment was started, and it was being first possible to rely on ultra high frequency signals broadcast, and it broadcasted data only. The Ethernet played an important role in the development of 802.11 standard, the first wireless standard. In the early 1980s, it became possible to use the Aloha random access techniques in both Wi-Fi and in mobile telephone networks. Aloha channels were used in limited way in the 1980s in 1G mobile phones for signaling and control purposes. In 2000s, additional Aloha channels were added to 2.5G and 3G mobile phones with the widespread introduction of General Packet Radio Services, that is the GPRS. Its starting date is the 2000, and we bring additional 2.5G and 3G mobile phones with widespread introduction of GPRS. This is a basic introduction. Now, wireless communication. The process of sending informations, voice, data, text between two or more points without the physical wire and cables. It utilizes electromagnetic waves such as radio waves, microwaves, or infrared signals to carry the data through the air. Includes cellular phone networks, Wi-Fi, Bluetooth, satellite communication, and infrared remote controls. These are all basic technologies of communication related to the wireless. The transmitted distance can be anywhere between few meters, for example, television's remote control, or the transmitted distance can be anywhere between thousands of kilometers for radio communications. These are the two different parts of communication range for the wireless system. Beside wireless technology include GPS units, radio receivers, satellite television, broadcast television, and cordless television, etc. Now, one by one, as the time goes, the new technologies, new devices are gradually adding with the wireless communication based on their distance ranges. Now, wireless communication advantage, very common: cost effectiveness, does not require elaborate physical infrastructure or maintenance practices, hence the cost is reduced. Flexibility, wireless communication enables people to communicate regardless of their location. Convenience, the wireless communication devices like mobile phones allow anyone to use them wherever they may be. Speed, the network connectivity or the accessibility were much improved in accuracy and speed. Accessibility, the wireless technology helps easily accessible as the remote areas where ground lines cannot be properly laid. And constant connectivity. Constant connectivity also ensures that people can respond to emergencies relatively quickly. So these are altogether the facilities, the pros we enjoy for the wireless communication. But I was in the Ericsson nearly around 96, 97. I was, hello, any voice cracking or is it audible? Sir?
Yes, sir. It is audible.
Audible. Can I continue?
Yes, sir. Yes, sir.
Okay. Now, during my first phase of my service life in Ericsson, we dedicatedly engaged for the wireless communication on the army. A long time, month after month, I stayed around the Chinese border, where I found that how the wireless systems can help the armies to communicate each other across such a dangerous mountain areas. And I was basically a quality control officer for the, and designer also, a part of the designer also for this communication kit. The quality control was directly related to the designs, PCB testing, wireless voice testings, noise testings, many things are there. And that we carried out at that high altitude areas, around 12,000, 14,000 feet. So this is the experience I just share with you. The types of wireless networks: wireless personal area network, wireless local area network, wireless metropolitan area network, and wireless wide area network. Now, WPAN is wireless personal area network, uh, covers a limited area around 10 meters or 15 meters like. WPAN is required a little infrastructure and often includes smaller personal devices like say Bluetooth, laptop, what we use where wireless computer devices such as keyboard, mouse, etc., wearables. This is a WPAN. Now, WLAN. A networking WLAN is a network that connects devices wirelessly using wireless LAN radio waves to form a localized area such as home, office, and campus. And every day we are acquainted with this type of communication. And WLANs primarily use the IEEE 802.11 standard, commonly known as Wi-Fi, and rely on access point to link wireless devices to the wired network. This is a very important thing. Wireless devices with the wired network. Wi-Fi is a common example of WLAN. WMAN, wireless metropolitan area network. This network provides a broadband internet access to people across larger areas compared to WLANs. WMANs operate on RFs and primarily use 802.16 wireless standard, generally as WiMAX. And WMAN, it covers a geographic area similar to a city. WMANs are larger than WLAN but smaller than W1. Now, this is another upgradation of the wireless network system. So WLAN is a cellular technology, basically, to provide wireless access. Cellular technology because the cells are arranged at a certain distance gap, and we develop and establish communication between the cells. So that's why WLANs use a cellular technology to provide wireless access outside the range of the wireless network. This type of network has an unlimited range and connects networks across large geographical areas. Since W1s use cellular technologies such as 4G LTE and 5G, they operate using cell towers. Now, wireless technologies transmit data over distance and without physical cables, utilizing electromagnetic waves like radio, microwave, and infrared signals. Infrared signals communication is another very important, up-to-date. Nowadays, many cases we are replacing the conventional way of communication in terms of infrared signals where it is feasible, at least from the wavelength point of view, from bandwidth point of view, from distance and all. So infrared signals is very popular kind of wireless communication part. And common examples include Wi-Fi, cellular for wide area mobility connectivity, mobile connectivity, Bluetooth for short range, etc. Now, key characteristics. Basically, it is restricted. The frequency band is restricted to 2.4 gigahertz to 5 gigahertz for Wi-Fi. Range distance varies from short range of Bluetooth to the wide coverage of cellular and satellite networks. Bandwidth, the capacity of the network to transmit data with higher bandwidth, enabling faster speed and power consumption. Some technologies are designed for low power uses, making them ideal for battery-operated IoT devices. The key characteristics of the wireless technologies. Now, the technologies, what we have just mentioned, just explaining one by one. What is Wi-Fi? Enables high-speed WLAN, allowing devices to connect a network and internet within a limited area. Cellular network, 3G, 4G, and 5G, which is very common term for all of us, especially 5G, and we are now entering the area of 6G. And very recently, I have found a few days back that China has developed 10G, where a movie of 3 hours can be downloaded just within 1 second. China has developed 10G technology that a movie can be downloaded within just 1 second, not within, but just 1 second. So how we are moving though it's a journal has given the news, but I just share with you. There is a China has developed a 10G part. You can search in the Google or some other media. Anyway, the Bluetooth, a short range technology used for WPAN to connect devices like headphones, keyboard, and smartphones. Satellite communication relies on artificial satellites to transmit signals, offering global coverage of communication. Infrared communication was saying this transmits data using pulses of invisible IR light waves for short distance, requiring a direct line of sight between the TX and RX, which is often an LED and a photodiode, respectively. And LoRaWAN and LiLP1, long range and low power technologies designed to connect IoT devices over a large distances with minimal power. It's a very notable thing. Whatever we do in the IoT part, we are extensively use the LoRaWAN and LP1. LoRaWAN is there is a specific chip we use, device we need to use for LoRaWAN and LP1. Very mindfully, you please observe this two term is very important for whenever you work with the IoT devices. Radio frequency identification use radio waves to identify and track tags attached to the objects, and ZigBee and Z-Wave. So another technology very important for us, low power and low data rate. Wireless technology is often used in smart home automation and IoT device also for low short distances. So ZigBee and Z-Wave, parallelly LoRaWAN and LP1, these technologies are extensively using right now, today's, for the IoT devices, because IoT is another important area where we connect the devices or things in terms of uh, some wireless technologies for signal received and signal transmit and processes, whatever, and IoT is very common term. So these two technologies has earned a lot of popularity for application from IoT device point of view. So thank you. This is the first slide I just complete for introduction to the wireless systems and its little history and the different technologies we are using in the wireless communication network as well as the communication process. So now, anybody else want to interact for this? Hello.
He has any queries, you can ask related to
The voice is not going very gradually going down.
anybody.
Maybe it is from my side. I don't know. My side is full sound.
Let me check.
Ha ha ha. Just. It was right initially.
Okay, sir.
Ha ha ha.
Uh,
Right now it's okay.
okay,
Right now
okay.
it's. Hmm.
Anybody has any queries regarding the background of this software-defined radio? You can ask. You are feel free to
Wireless
ask.
communications.
Yes.
Uh,
I think, sir.
I think there is a chat.
Okay.
Somebody has written something in the chat box.
No, sir. Still now, nothing in the chat box. So, sir, you can
You
continue.
can proceed. I can proceed.
ఒక నిమిషం ఆగరా నా ఉండు.
Okay.
Okay, sir, you can continue.
Okay, very good. Now we are going to the next phase of the slides, where we'll explain SDR and the basic architecture for this. It's very interesting for us. Slides are audible.
Yes, sir, visible, sir.
Visible. Very good.
Okay.
The software-driven radio and the a new landscape in the wireless communication. Hopefully, I think those participants, maximum participants may be acquainted with the SDR, and may some of them maybe have hands-on experience of working in their research for the wireless communication in terms of the software-defined radio. Initially, what happens? Now, it's a basic introduction of the software-defined radio. What it is actually, why it is so popular nowadays, and where the almost every communication lab, the SDR is mandatory, and without this unit, no such experiments nowadays is valid at all. But how it comes? What is the activity and what's the background of this software-defined radio? The software-defined radio is a type of radio communication system, definitely, that uses software to perform functions that are typically carried out by hardware. In the previous case, we also, in our time, we also carried out our lab experiments in terms of some mixtures, filters, amplifiers, modulators, all other hardware, physical existence of mixtures, filters, amplifiers we used for the experiment. But nowadays, that all hardware, very costly hardware, has been fully depleted in terms of software. Definitely, we are using a particular hardware, obviously. We are mixing the software with the existing hardware, FPGA hardware. Obviously, this is a hardware, but the hardware is not a very specific kind of mixtures, filters, amplifiers, demodulator, modulator, not that. It's a common chip, common hardware mixed with the software. And we are developing all kind of protocols, all kind of experiments of communication using this single hardware. That you don't need a very big lab, which we required in our say 90s and 80s. This is the main significance why we are using SDR. The next point, in traditional radios, key operations such as modulation, demodulation, and signal processing are handled by physical components. However, in SDR, these tasks are executed through software, allowing for easy reconfiguration and updates. The reconfiguration and updates are the two words is very, very important for the SDR. The single hardware, but we are able to perform multiple type of modulation technique, digital, analog, whatnot. All 5G experiments, all 6G experiment, all type of radar, all type of signal processing, we can do using the single hardware. So it's a great discovery in terms of wireless communication. So that's why today's heading is the SDR and Advanced Wireless Communication System. Why it is advanced? Because of this, it is advanced. This means that SDR can support wide range of frequencies and protocols without needing to change the hardware. Hardware is a single hardware, but only we are changing in the software. And the coding, basically the coding. So whenever we are flexible with the coding, whenever we can able to do coding, then everything is within our control. It effectively transforms a personal computer into a versatile radio device because the software is installed in the laptop, in the desktop, as if it is a radio unit, and we are making our all kind of software programming, programming configuration for digital modulation, for analog modulation, for DSP, the signal processing, everything in terms of software, and we are downloading into the hardware, and that hardware in terms of antenna transmits, receives basic functions. But the hardware is a single one. In essence, SDR provides a flexible, cost-effective solution for modern communication needs. The history and evolution, software-defined radio emerged in the late 1970s and 1980s from US and European Defense Research Organization. The aim was to develop flexible programmable radio systems evolving from hardware components to processing radio functions via software. The advancement in semiconductor technology allowed SDR to be implemented on smaller or more efficient platforms. Today, SDR is a very dominant standard, enabling agile, intelligent communication systems by shifting signal processing functions from hardware to software. This is the most important part, hardware to software. So what was initially in terms of hardware, there are table after table and students are sitting, researchers are sitting for a long, occupying long, maximum area in the lab. We don't need anything like this. Only you need a computer, only you need your software and the radio set and few antennas, and within a very limited space, you can develop all gigantic type of communication systems, programs by this SDR. So that's why intelligent communication system by shifting the signal processing functions from hardware to software. All Fourier transform or Laplace, all required, if required up there. The Fourier is maximum use for this. You can do it. Its evolution reflects a broader trend in technology towards software-driven solutions. It highlighting its role as a cornerstone in the future of communication. It has an already implemented and already proved and established. While software-defined radio shifts many functions to software, essential hardware components still play in a vital role. At the core of SDR, in the radio frequency front end, is the radio frequency front end, and which includes antennas, amplifiers, and definitely there. I'll show you the picture of SDR. Definitely the SDR may be a box, single box, but there are inside this, there are the antennas, connection points, amplifiers are there, filters are there, but only single. These components are crucial for receiving and transmitting signals. The RF front end is responsible for converting analog signals from the air into digital data, the ADC part, during the ADC part, and that can be processed by software. This analog conversion is necessary for digital signal processing unit of the SDR. Conversely, digital to analog converter, that is a DAC also, is used for converting the processed digital signals back into the analog for transmission. Lastly, a powerful processor is required to handle the complex computations involved in signal processing. At the heart of SDR, software. SDR software is the digital signal processing unit which manages the conversion and manipulation of signals. This unit allows implementation of various modulation methods, demodulation methods. These are the basic scheme of communications, enabling the radio to support multiple communication standards. The flexibility of SDR stems from its software component, which can be updated or replaced to accommodate new protocols and features. The software architecture often includes a user interface layer. There are some physical layers, obviously, and every layer we can use for this SDR purpose, which is crucial for configuring the SDR to meet specific communication requirement. Open source frameworks and the libraries, like the GNU Radio, have further propelled SDR development by offering ready-made tools for designing and testing radio systems. GNU tools basically icon-based software, and it's a free software, and it's very flexible for making all type of communication protocols, developing, and all type of communication modulation purpose. We can use GNU Radio. GNU Radio is a very popular software and user-friendly as well. Okay. The software-defined radio as a technology enables communication system to be implemented in software rather than through specialized hardware. That means you do not know, it do not require to make some special kind of mixture, filter, modulation devices, not that. The single one hardware is there, specialized hardware is there, specialized OEM, several OEMs are there, Rhodes are there, NI, National Instruments are there, ATAL Pluto is there. Many radio SDR manufacturers are there. Rhodes is one of the largest, biggest, and specialized for their communication device. I always prefer the Rhodes unit because I have worked with the Rhodes unit while I was worked directly with the defense sector, Indian defense, during my initial starting of my life around 96, 97. SDR involves the use of software to control radio frequency hardware such as transceivers, amplifiers, and antennas. By controlling these hardware components through software, SDR systems can adapt to changing environments and operate across wide range of frequencies and modulation schemes. Because there are some options, I will show you the NI hardware software, LabVIEW software, and you will get a little idea about it. SDR is a radio that has the ability to be transformed through the use of software and redefinable logic. So particular software you made for a particular modulation, and you can just redefine it, change the software, and you will get another type of modulation, another type of frequency range, and another modulation index. You can flexibly change it. That's why one of the primary benefits of SDR is the flexibility. Okay. The traditional radio communication systems are typically implemented using fixed hardware that is designed to operate at specific frequency and specific modulation scheme. This makes it difficult to adapt a changing requirement or to support multiple communication protocols. That is the limitation of the conventional communication lab then compared to the advanced wireless communication lab. It's difficult to adapt to changing requirement and support multiple communication protocols. The second point and the first point is the specific frequencies and specific modulation schemes only for the fixed hardware part. So there are two limitations. One is fixed hardware, another is difficult to changing requirement to support or to support multiple communication protocols. Now we are entering into the SDR that we have discussed just now. In contrast, SDR systems can be reconfigured in software to support different frequencies and modulation schemes. It's a very interesting part. This means that single SDR system can be used to implement multiple communication protocols or adapt a changing to requirement in the real time. It's a picture of a SDR. There are two parts. One, there are two openings over there for connecting the antennas, and there is some other separate part you can connect with your laptop PC based on the software. You can program it. Now, architecture of SDR basic parts. Radio frequency unit is there. Analog to digital or digital to analog converter is there. Mixtures are there used in up conversion and down conversion. Modulator, demodulator are there. Amplifier, filters are there. All are actually based on single PCBs and accommodated within a box. Now see the SDR versus analog receiver. In the upper part, there is the previous conventional way of receiving the signal, antenna, band pass filter, RF amplifier. We know everybody in our communication lab, we use this type of different type of devices like the local oscillator we are sending, and then the mixing, and IF amplifier, filter, demodulator, and finally audio amplifier. But in the below diagram, you see it is the SDR. antenna, RF amplifier, RF tuner, all actually based on a single chip or some single PCBs, but in a single unit, not separate IF amplifier, demodulator, not like this. It is a single unit. In the below, I'm showing you the software-defined radio receiver. Clear? Now the transmitter architecture for SDR. Signal DSP signals are coming, and digital up converter here. Digital IF samples are there. Analog signals, analog RF signals, and power amplifier. And it is going transmission part. If it is transmission part, then the receiver part is like this. So received signal, and it is processed as per the inside design architecture of the SDR, and finally it enters into the SDR for signal processing. So these are the transmitter architecture, receiver architecture. Definitely based on the OEMs, the architecture is vary, but the basic thing is this. The modern SDR implements often extend this concept to encompass the entire PHY layer and RF chain within the software. All PHY layer for communications. There are 7 PHY layer almost available. So that 7 PHY layer, application layer, presentation layer, sensing layer, many layers are there. Transport layer, network layers, data link layer, and physical layer. These layers are already configurable in the SDR. SDR-based designs are increasingly prevalent in WLAN, mobile, WiMAX, 4G LTE, LTE advanced long-term evolution, that's the LTE, that's the 4G, and 5G in our new radio. SDR is a wireless device that typically consists of configurable RF front-end with an FPGA or programmable system on chip to perform digital functions. What I'm showing you, all the FPGA. In the previous case, if you go there, you see digital mixture, low pass filter, digital local oscillators. Basically, these all are FPGA programmable SoC. Clear? So that's why it's a single hardware. Wireless engineers can use software-defined radio hardware as cost-effective, real-time platform for a range of wireless engineering tasks. So different wireless engineering tasks we carry out with this SDR. What are those? Then over-the-air lab and field testing with live RF signals. Those who are a little bit acquainted with OTA, I mean over-the-air communication and the different type of advanced research, they will be able to understand the 3 points very carefully. Then rapid prototyping of custom radio functions and hands-on learning of wireless communication concept and design skills. These are the main 3 type of things in the real time platform for executing the experiments of in terms of using the SDR. Now MATLAB and SDR. I should say that nowadays we are using MATLAB extensively for SDR. Maximum OEMs make their SDR compatible with the MATLAB function, MATLAB connectivity. May not be many, but maximum I have found that without one maximum NITs and IITs prefer to write their programs in the MATLAB rather than the OEM's own software, because MATLAB is a general purpose kind of software we use from the very beginning in our engineering course. So everybody is quite acquainted with the MATLAB codes and process. So MATLAB is a kind of software which we using this. Even we can, everybody knows that MATLAB and Arduino, we can connect and we can make different type of programs. Instead of Arduino IDE, we can make our program in the MATLAB and we can download in the Arduino. And For that, MATLAB is very, very user-friendly from this. But MATLAB code, you have to write licensed software is required for doing the MATLAB code. So MATLAB and SDR is a neck to neck. Without using MATLAB and Simulink, you can develop lots of interesting programs and for your research purpose. So wireless engineers can also work with various wireless standards such as 5G, LTE, WLAN, DVB-S2, users SDR and others using SDR and MATLAB connectivity. Digital video broadcasting satellite second generation signal is a physical layer standard to support high data rate in the satellite in space. And actually DVB-S2 has a special library in the MATLAB to work with the satellite second generation physical layer signals. It provides the specifications for framing, structure, channel coding, modulation systems, and spectrum efficiency. You see the SDR is this, and it is connected with the MATLAB. That is the host computer have the MATLAB, and there's Ethernet. Either you can connect the host computer with SDR through Ethernet or USB or PCIe, extended PCIe. And you will enjoy the programming of SDR using the MATLAB. So I will recommend everybody to do their work using MATLAB, whatever the SDR may be. It may be from the British words, it may be from the Hinai National Instruments. You have the facility to work with using the MATLAB for SDR. Using a software-defined radio together with MATLAB and Simulink for wireless design, simulation, and analysis enables engineers and students to do what type of kind of experiment? Transmit and receive standards based on customs generated signals. There are separate libraries in the Simulink. Test designs in presence of interference and other real-world conditions. Perform real-time signal analysis and measurement. Deploy, prototype, and verify custom designs on Xilinx radios using HDL and C code generation from algorithm models. So Xilinx radios, Xilinx FPGA chip. So using the if the radios
চাকরি মহিলা বাড়ি যাও আপডেট করতে হবে সব সময় না
Okay, sir, please continue.
Okay. So Xilinx radios using HDL and C code. HDL code is very important for the MATLAB, and C code also is that you can write your programs, I mean prototype and deploy this using the Xilinx radio SDR for HDL C code generation from the algorithm models. Now, generate HDL code from Simulink models and deploy on supported USRP. USRP is the SDR from the National Instrument radios. Verify implementation, and what more we can do? The verify implementation in the radio in loop tests. So what is radio in loop test? Radio in loop test can refer to testing a radio's ability to transmit and receive signals by sending the output back to its input, often using a loopback adapter or translator to verify the transceiver's functionality. I mean, transmitter receiver functionality you can check using the radio loop test, and that can be performed by coding or in terms of MATLAB using Simulink. And this is a very popular test for the radio test, radio loop test, very important for SDR. Here is a commercial SDR I have shown you. It's connected with the PC workstation by USB or any other way of communication cable. And the MATLAB communication toolbox here. You can write your program in Python C programming process. So whatever loop, maybe loop test or maybe modulation or anything you write in the MATLAB, you can write in your MATLAB, which is installed in your PC or workstation, and connect it directly to the commercial SDR boards for performing the communication protocols or modulation technique, whatever. Transmit and capture signals to be tested wideband wireless systems and perform spectrum monitoring. That is also possible to write in the MATLAB using the MATLAB and SDR. Transmit and capture signals to test wideband wireless systems and perform spectrum monitoring. Generate HDL code from Simulink models and deploy on supported USRP radios. Verify implementation. Just a minute. First few lines are common. In the last line, the capture wideband is, and now is another model I am showing you, that ARM and FPGA, ARM board, okay? ARM C and HDL codes you can write here. You can connect, you can do it by using the MATLAB Simulink, and you can directly connect to the HDR. Okay. So, now, you can use MATLAB and Simulink to communicate with several popular SDR platforms to perform radio in loop test testing, prototyping, and hands-on learning, which is the radio sets I have mentioned over here. Is the analog devices ATAL and Pluto. ATAL and Pluto is a very popular radio device, and it is directly compatible with the MATLAB, which is I have just given you a picture over here. You see, this is a SDR platform, is the ATAL and Pluto. Then NI, USRP, B2XX, N2XX radio sets, USRP, all these are from the NI brand, B210, N210, N2310. So X series, X4 series, these are advanced radio sets from the National Instruments. And RTL is a radio set, very cheap radio set, almost 1.7 gigahertz frequency it can cover. You can use for low cost. If you want to purchase a low cost SDR, you can easily purchase RTL SDR. It is also available in the Amazon. Directly you can purchase it for your experiment purpose. So local broadcast FM radio station, here you see it is the over the air signals are coming in the Pluto, and it is processed by the MATLAB baseband file. So Pluto is a very popular radio set, relatively moderate price. Next, another local LTE antenna here over the air. Signals are coming to the SDR USRP E310, is a National Instruments SDR, and we are making our programs using the MATLAB. So these are the different radio sets. This is the ATAL and Pluto. This is the NI USRP. This is the RTL, and this is the SOC. This is a more complicated, but this type of things nowadays not enough popular. But popular is this white box NI USRP and the ATAL and Pluto. And sometimes for the very low cost SDR, if you want to use, you can use this. I mean the RTL SDR. That's the MATLAB code for tracking track planes by processing automatic dependent surveillance broadcast signals. These models we have developed. Once we have developed, and that's I'm showing you over here. So if you go to the Simulink in MATLAB, and there are some specific blocks available, and using the blocks you can develop this type of tracking system for airplanes. The advantage of SDR: flexibility and reconfigurability. Definitely easily adaptable of new communication standard and protocols. Cost savings, reduced need of dedicated hardware for each application. Rapid prototyping enables faster development and testing of new wireless technologies. Customization allows for implementation of unique waveforms and signal processing algorithms. This is the customization process, which is important. And remote upgradability. Software updates can be developed over the air, avoiding the need for hardware replacement. Applications: wireless communication enables development and testing of various wireless communication systems. 5G LTE, 5G LTE 6G, we are dedicatedly use this SDR nowadays. Radar systems can be used for developing and testing radar systems, including those for weather monitoring, traffic control, etc. Cognitive radio enables radio to sense and adapt to the environment, optimizing spectrum uses. Amateur radio, scientific research, astronomy, space exploration, atmospheric science. That is the all are advanced communication systems. How advanced communication systems, the term comes into the technology by through the SDR that I want to highlight over here. Electronic warfare can be used for signal intelligence, jamming, and other electronic warfare. Military communications, SDR can provide secure and flexible communication systems for military operations. Now in defense, Indian defense extensively use SDR as using for their communication device instead of old or previous sets. Public safety SDR can be used to emergency response, such as the police, firefighters, and paramedics to communicate during disasters or emergencies. Broadcasting SDR can be useful for broadcasting to improve the quality of transmission and allow for the delivery of multiple services over a single frequency band. Satellite communication. Using satellite communication, SDR can be used in satellite communication to improve the flexibility of the communication system. IoT. SDR can be used in IoT applications to enable communications between devices and improve the efficiency of the network. Many institutions and organizations nowadays interested for launch a kind of workshop or training systems using SDR as a base station for IoT technology. We're using SDR as a base station for connectivity of the all type of things around us through single SDR, because SDR in that case is using as a base station, and we are connecting the all such IoT devices through a single SDR. That's a very important thing over here. Radar SDR can be used in radar systems such as weather radar that we have already just mentioned. But the limitations, along with the advantage and pros, what are the cons of the SDR? The computational power requirement. SDR requires significant computational power to handle real-time signal processing. But nowadays, research are going in such a space that power is already been arrested, and it has been reduced significantly than the previous SDRs. Sensitivity to interference. SDRs are more susceptible to interference from other radio sources because of use of software to control the radio. Another limitation is the susceptibility of the noises or some other radio signals. Latency. SDR systems require a certain amount of time to process signals, which can lead to latency issues, and this delay can cause problems in voice or video communication. These are general type of limitations, but research are going on to reduce all these limitations to almost zero level. But these are the common limitations. That one or two or three limitations might be there, but it does not hamper the process of SDR or signal synthesis. Complexity. SDR technology is more complex than traditional radio system. Definitely, your code, you are practically writing the software code is for that you need very skilled software developer, very skilled software developer. Otherwise, it is difficult for ordinary person to make a modulation scheme in terms of software. Definitely. So that's why more complex than traditional radio systems. In the traditional radio system, what do we do? We connect this wire to that, this wire to that point, this point, that point, and give a switch, then started, and transmission starts, receiving starts like this. But here you are making entire software. So definitely you need a lot of skill and knowledge for developing this thing. It may be you can make it under limitations or something else as per the users. While the cost of SDR hardware has decreased in recent years, it is still more expensive than traditional radio systems. Security, as SDR is entirely software based, it may be susceptible to hacking or other security threats. But nowadays, the devices are making such a way that the security devices are far more, or many firewalls are embedded into the hardware so that the security issues are considerably reduced. So thank you for the second part of introduction and applications of SDR. If anybody else wants to discuss anything, you can ask. Otherwise, I will go to the next slides.
Anybody have any queries? You can ask, sir.
If not, I can go to the next phase of the slides.
Okay, sir. Please go on.
Okay, thank you. Okay, thank you. I'm going to the last slides, which is the advanced wireless system using SDR. And these slides are the advanced wireless communication research lab. That is the last phase of this seminar, I mean for the lecture. Is visible, sir?
Yes, sir, it is visible.
Visible, good. Now, these very complex processes I wanted to represent over here. The mobile connections, Wi-Fi, data transfer, satellite connections, data transfer from the router to the tab and to the some other devices, many things, mobile phones and etc. The introduction to advanced wireless system. We have advanced SDR, we have lab, we have discussed, but advanced wireless system. Advanced wireless communication refers to cutting edge technologies and techniques built upon fundamental wireless principles to enable faster, more reliable, and diverse connectivity. The wireless ecosystem often integrating with artificial intelligence, cyber security, and sensor systems for IoT applications. Very important thing, please carefully note it. Artificial intelligence, we are connecting with SDR, cyber security, and sensor systems for IoT. IoT and 5G, when there is a IoT 5G combinations are there, and we can execute all this by means of SDR. The key example include 5G and beyond, I think which 5GB, 5G and 5GB, that is 5G and 5G beyond, cellular networks, advanced Wi-Fi protocols and technologies like Li-Fi, light fidelity, which utilize new spectrums. These are the advanced kind of thing in the wireless systems. These technologies utilize new spectrums, sophisticated algorithms, and innovative architectures to support high-definition streaming, real-time data, and vast number of connected devices. Vast number of connected devices is a very important thing. Researchers in the area are exploring optimizing wireless network performance, adaptability, and coverage by integrating new technologies such as cognitive radio, machine learning, and reconfigurable intelligent surface. So these are the advanced wireless system topics. These are the advanced wireless communication lab specializes in conducting research in the broad area of wireless communications, which with a focus on signal processing with the physical layer. That the layer which I just mentioned over here. The primary research activities include signal processing for a wireless communication system, cognitive radio, dynamic resource allocation, and cognitive radio uses DRA to intelligently find and use available spectrum opportunities from primary users to secondary users. I'm not discussing whether there is no scope of discussion in detail of the cognitive radio, but just for the idea, I just given you the cognitive radio uses DRA, dynamic resource allocation, It's a big topic over here. Full duplex radio or hardware-based modeling and signal processing techniques. These are the primary research activities, which is under wireless communication, advanced wireless communication research lab. What we do in the lab, what type of research we carry out in the lab, which is advanced. These are the headings: signal processing, cognitive radio, full duplex radio, software radio, USRP experiment and implementation, hybrid beamforming, FDM or OTFS, just like OTFS means orthogonal time frequency space modulation, has recently been identified as a suitable waveform for joint radar and communication systems. Okay, OFDM and OTFS, very joint radar and communication system, JRC. We're using these two techniques. One is OFDM is previously, now it is OTFS. Orthogonal time and orthogonal frequency. MIMO OFDM systems, this is channel estimation is one of the important part for this. Radar, radio detection and ranging, signal processing. That means I want to mention here that in advanced research lab, by means of advanced SDR and vector signal generator and spectrum analyzer, using these as a whole, we can develop this type of most advanced type of topics like say beamforming, MIMO OFDM systems in an advanced communication lab. Now the AWC lab is equipped with a state-of-the-art equipment and development tools designed for real-time signal processing and communication. That is the AWC. The lab's comprehensive setup enables advanced research and development, fostering innovations that push the boundaries of current wireless communication technology. So what are these? The lab, research lab, what are the hardware we need for developing this? First is the universal software radio peripherals, that is USRP, or any such other relevant SDRs or transceivers. In case here, I just mentioned one of the SDRs from NI, National Instrument, which is USRP N210, carrier frequency from 6 Hz, sub 6 gigahertz, and bandwidth is almost 20 megahertz. Daughter cards, that is LFRX DC 30 megahertz daughter card, octoclock generated GPS antenna. Let's see the other type of hardwares: vertical antenna, ATAL Pluto device, PXP generator, channel emulator from Keysight, EXA spectrum analyzer, MXG vector signal generator, RF development tools, AD936 for software development board, like this. So what are these? These are the advanced communication devices which is need along with the SDR for developing such experiments, say beamforming, OFDM, MIMO, etc., etc., etc. So that's why it is wireless communication and advanced wireless communication. Why it is advanced? Because of these. Now let's see the one by one pictures. You will get an idea. LFRX daughter board for USRP. That means this daughter board you can connect with the N210 USRP for various type of signals, synthesis and processing, or giving signals from the outside. These are basically the USRP power supply, antenna, and all these things. This is another USRP board. I mean, from other OEM, not from National Instruments. This is the octoclock generator distribution device, help researchers to synchronize systems and include NI USRP devices. This particular device, you can connect 2 or more USRP for synchronization, for developing the MIMO experiment, that is multiple input, multiple output experiments. So octoclock generator is a very important thing for synchronization purpose. Next, you see GPS antenna. That's a separate thing. If you want, you can use the GPS antenna. Instead of this NI-USRP, you can use SDR from the ATAL and Pluto. You can use PXP baseband generator and channel emulator from the Keysight. Keysight and Rodeshwartz are the two globally renowned communication manufacturer OEMs. And definitely there are some others also, but these are very known. All IT and ITs are packed with Keysight devices. The EXA signal analyzer, for analyzing the signal, there are separate softwares are there. You can install it. Sometimes you need to install, or sometimes it is basically a computer-based signal analyzer. All such peaks and all these things you can analyze over here. Up to 44 gigahertz you need. Next, you can RF vector signal generator for IQ signal observations. Then AD, FMC, FMCOM, MS4 EBZ is a high-speed 1x1 agile RF transceiver analog FMC module, software tunable over 56 megahertz and 6 gigahertz. Then there are connectors are there. With this connector, you can connect either with the signal generator or vector signal generator. You can transmit signals from the SDR. You can receive it and process it using these all various types of communication devices. Now, at this stage, this is the last slides I am presenting here. In the last slides, I am showing you the dedicated hardwares for the advanced or the modern wireless communication research lab. Without this, it cannot be done. Now see a setup for this. This experiment I performed in one lab in NIT Rourkela, probably so. The transmitter receivers are there. The distance almost 1 meter. At a distance of 1 meter, signal transmission and receive. It was a signal of say, 4 QM, quadrature amplitude modulation, that we have performed. I'm showing you the lab setup for this. The two SDRs are there, and these SDRs are connected through Ethernet cable. And you are using, since it is national instruments, you are using the LabVIEW software and some special APIs to communicate between the to transmit and receive the signals. You can use also using a single SDR for transmission and receive. Here I used two separate SDR for transmission and receive. Now these are hello.
Hello,
Now
sir.
these are
Please go on.
now this is the code for LabVIEW. These are the APIs using in the sorry. These are the particular API that open transmission session, TX session, configure signals, and within the loop, the signals is processed and ultimately is go out. And these are the parameters we have set. The several frequencies, the IQ rate is there, carrier frequency are there, gain are there. These are the basically the block diagram for transmission purpose. And for receiver purpose, this block diagram is there. These APIs are available in NI USRP, NI software, which is separately to be installed here, over there. And you can configure your, that's why I said that you can.
1 minute, sir. Am I audible to you, sir? 1 minute, please, sir. Sorry for the interruption. Uh, Sir, just 1 minute.
Hello. So now can I proceed to?
Yes, sir, you can proceed, sir.
So now almost in the last phase we are discussing. So all types of analog and digital modulations, few applications. First is the all types of analog digital modulations. Next is the channel sounding. CS is the method of estimating distances between the two devices, designated as initiator and the reflector. Just in a small line, I just want to explain. Channel sounding, spectrum sensing with the USRP involves to capture RF signals and then employing algorithms, often in GNU radio or the MATLAB, to detect presence, absence, or characteristics of these signals in the radio spectrum. So radio spectrum sensing is another application area. I mean, the research part. Cognitive radio is an emerging technology that enables efficient utilization of the spectrum. Beamforming and massive MIMO. Beamforming and MU-MIMO means multi-user MIMO work together to deliver 5G's demanding throughput and connection densities. In the 5G, the connection density is 1,000 devices per square kilometer. And OFDM, advanced signal coding technique, VLC, visible light communication, beam steering, video transfer over PHY using OAI and over-the-air interface. 5G VLX test bed refers to a 5G vehicle to everything test bed. The primary goal is to test communication between vehicles and other entities like infrastructure or pedestrians using 5G technology. Now VLX and VLC are the two very booming technology nowadays. We are using this type of research are going on the VLC, visible light communication, beam steering, and 5G VLX testbed. Interoperability testing between two separate locations using GNB and UE. GNB for 5G NR base station and UE user equipment, 5G NR user equipment.
Sir,
Remote
just for an interruption, people are telling that they are not, the presentation is not visible actually. They want to see the
not visible.
PPT. Yes, sir.
Oh my
PPT is
God.
not
Oh,
visible.
just a minute. Very sorry.
Okay. Okay.
Oh, I just once again. But it is under sharing.
Sir,
Just a minute. It is under sharing, but if the sharing part is inactive here. Presentation is not shown. Somebody's legation is given. Sharma Ushoshi Sarkar. But thing is this here, I cannot just a minute.
You do stop sharing and again please share.
Stop sharing is not activated here. Whenever I only meeting organization presentation can share. Achha.
Okay. 1 minute, sir.
Just a minute. Can I leave and again join?
Yes, sir. Yes, sir. You can do that.
Okay. Just a minute. Let's see. Now I think it is.
Yes, sir. It
visible.
is visible now.
Just a minute. This. So VLC, it is visible. Now the VLC part. Now once again, I am just repeating this. A few applications over here. All types of analog digital modulations, channel sounding, spectrum sensing, cognitive radio, beamforming. These are the big projects practically you can do using the SDRs. That's why I'm just mentioning the name. And I just explain a few lines or sentence what the actual topic signifies, like say channel sounding. It's the estimating distances between the two devices. Spectrum sensing, capture RF signals and then employing algorithms to detect presence, absence of the characteristics. So signal spectrum is what spectrum you want, whether present or absent. cognitive radio is very selective or efficient utilization of the spectrum. Beamforming and massive MIMO is a big infrastructure you need. At least you see, if you develop a 2x2 or 4x4 MIMO, then you need at least 2 or 4 SDRs for this experiment. Beamforming and multi-user MIMO work together to deliver 5G's demanding throughput and connection densities. OFDM, advanced signal coding technique. Now, one more thing I want to mention for beamforming and massive MIMO for cognitive radio. If you go through Rode-Schwartz vector signal generator, then you can perform all these things with a single unit. But it is very costly, almost nearly 2 CR, 2 crores is a price of this device. But still, instead of this, if you want to develop in the low cost, you can take at least 2 or 4 SDRs and connect the antennas so that either 4x4 or 4x4 or 2x2 MIMO beamforming you can easily develop with a very low cost in your lab. Now, what I was discussing, VLC, visible light communication, beam steering, video transfer over PHY and OAI, VG VLX test bed. Actually, these two particular tests, VLC and 5G VLX, is a very dedicated type of research activities is going on in the IISc Communication Lab, Indian Institute of Science, Bangalore. Once I got from a journal, I found these two type of research activities, and that's why I mentioned over here. Now it has been developed successfully. Now, interoperability and testing between the two separate locations using GNB and UE. That is a part of SDR. You can use geographical node you can develop. G node B was previously E node B in 4G LTE, and it was node B in 3G. So now 5G, it is GNB, and UE is a user interface. So all are the 5G inner experiments. Remote vehicular control over LTE and Wi-Fi. Over the air, TX and RX in millimeter wave, almost 300 to 300 gigahertz range. Definitely, you can select a little less range than 24 gigahertz or 26 gigahertz or 6 gigahertz for developing this thing. And downlink transmission over 80 megahertz bandwidth. So these are the overall lecture session, seminar session about the Advanced Wireless Communication Research Lab. And as a whole, today's heading was software-defined radio in Advanced Wireless Communication System. Now, these are the videos which PPTs I showed you from this point of view, and I'm going to here just a minute. So this is the end of this session. And if you have any interactive questions regarding the presentation overall, then we can do for just 1 or 2 minutes, 1 or 2 questions I can take. And lastly, I just, how can I give the questions, sir?
Sir, you can show it in the slide. PPT slide.
Oh, in the slide.
Yes, sir.
Actually, not. It is available in the slide.
So,
can I write in the
give it in the chat box also?
Chat box. Very simple questions I am
Or,
writing here for the student level. What you have told me. Okay.
Okay, sir.
I'm just writing.
Or you can mail me also. You can email me also.
Right now or later?
Later. You can. The question answer session for this session 7. Is there anybody want to ask something related to this topic to Joydeep sir? You are free to ask him. Please
If you
go
have
on.
any questions, you can write in the chat box also. Okay, I'm sending the.
Okay,
Hello.
sir, you can mail me it later. And
Acha, okay.
thank you, sir.
Okay, I'll mail it to later.
Yes, sir. Thank you, sir, for your informative session on software-defined radio in advanced wireless communication domain.
Thank you.
And we are privileged to have you. And we have some small token of greeting for you, a small memento. Please, sir,
Okay.
accept it, and we'll send you this via
Thank
mail
you.
later. This is for
Okay.
you. Please, sir, accept it on behalf of your institution.
Thank you. Thank you. Thank you.
Okay, sir.
I'm very glad for this memento.
Okay, sir.
Thank you.
Thank you. Thank you, sir. Thank you.
You will send me over email
I'll
or.
send you in the email of your email ID.
Thank you, sir. Thank you.
Okay, sir. Thank you, Joydeep sir, for your informative session on software-defined radio.